Notes 4.4, solve polynomials by factoring. We're actually going to concentrate on the factoring portion of this today, and we'll continue to look at how we can solve polynomials next week. Tomorrow will be an opportunity in class for you to work on practicing with your factoring and sort of tweaking your factoring skill. So the first thing that we're going to talk about on the solve by factoring notes is, of course, how to factor different types of polynomials. So the first things that we're going to discuss are going to be the special patterns. Okay? So these are our special factor patterns. Thanks, Jason. The first one we'll talk about, the difference of perfect squares, you already know. We learned that last chapter. I'll put it up here on the board so you can copy it in your notes. And it's that first one we saw on the screen of the previous slide. A squared minus b squared we'll factor out as a minus b times a plus b. And you can switch those two around. It could be a plus b times a minus b. Multiplication is commutative, so it doesn't matter. In that example, a and b must be the square roots, correct? Okay, so if you want to write a note to yourself in the margins or near that problem, where a and b are the square roots of the perfect squares. So that one's pretty simple. We can use that one still with polynomials. We always want to check for that difference of perfect squares. Now, there is not a sum of perfect squares factoring, like x squared plus 9. We looked at that when we solved quadratics last chapter. If we were to solve x squared plus 9, the two solutions would be positive 3i and negative 3i. So sum of squares has imaginary solutions, therefore does not factor. Now, the two new ones that you're responsible for will be the sum or difference of perfect cubes. Okay? Unlike the perfect squares, we can factor both operations with perfect cubes. Okay, so if we have a sum of perfect cubes, it's factorable. If we have a difference of perfect cubes, it's also factorable. They're the same rules that we uncovered in small groups by expanding. If you expand a minus b times the quantity a squared plus ab plus b squared, the only terms that will remain will be the perfect cubes, a cubed minus b cubed. All the other terms in your expansion will cancel out. So then we can use that as our special factor rule. You're responsible for knowing this rule. So when you think about like things that you might study for math, things that you might go back and look at, sum and difference of cubes would be one of them. And then we also have the sum of cubes. A cubed plus b cubed is equal to a plus b times the quantity a squared minus ab plus b squared. Make sure that you double check that you copied these correctly with the correct signs. Now, you are responsible for knowing the formulas for special factoring of sum and difference of perfect cubes, but paying attention to patterns can really help you out here. So tell me, what are some similarities between the two factor patterns? Can You notice anything that's like the same, Reagan?
When it says a squared minus b squared, that's there's a minus sign in between a and b, and then there's plus and then plus sign.
Oh, great. So you said squared, but I would change it to the cubes, right? When it's a cubed minus b cubed, this always matches that very first sign for a minus b. And then when it's a cubed plus b cubed, that matches a plus b. Okay, so that's really helpful. Okay, the first sign matches. Hannah?
The first sign and the third sign are opposites. So when you like subtract, if you're adding a plus b, you're going to subtract ab.
Oh, okay, so like this one, this matches the original problem, but then the third one is the opposite. Okay, so it's opposite of what we had in the first group. And then same goes here too, right? Okay, when it was plus and plus, then we get a minus right there. Okay? And what else do you notice here?
The square number is always positive.
Oh, the one at the back is always plus. Okay, so this, you're talking about the b squared term, right? Okay, the b squared term will always be positive. Excellent. So you've uncovered my special way to remember the sum and difference of perfect cubes, which I call SOAP. SOAP stands for same, opposite, always positive. That's the rule for the signs. Same, opposite, always positive. So if you have a difference of perfect cubes, like a cubed minus b cubed, the first sign that you write will be a minus sign because you keep the same sign. The second sign will be the opposite, so it'll be a plus. And the third sign, like Sierra said, will always be plus. And then if you're doing a sum of cubes, it's originally a plus sign because it's a sum. So when I factor it, my signs will be same, plus, opposite, minus, always positive. Okay. And then the other thing that those factors have in common is they're the same terms, right? An A squared, AB term, and a B squared term. So if you can remember the terms, then all you have to do is remember SOAP. Cool? Now some people will say mop, match, opposite, positive. If you don't like SOAP, do mop. And there might be one other one that I don't remember. Any questions? Okay, can you work in small groups for a little bit and see if you can decide which one of those special factor patterns you should use for these three problems? And can you decide like what your A and your B are? Can you plug that into the special factor pattern? We'll check our work here in just a moment. Okay, but we've got x squared minus 25, we've got x cubed minus 27, and then we have 4x to 6 minus 49. So go ahead and work on those for just a couple minutes, and then we'll come back together and we'll talk about them. Okay, excellent work. So I've got TJ, Hannah, and Andrew offered some ideas for us. TJ, you decided this was what kind of special factor pattern? Yeah. Just factoring, like which one? Difference of squares, sum of cubes, difference of cubes. Yes, this is a difference of squares. And so you notice squares. You notice that x squared is a perfect square and 25 is a perfect square. Remember that when you put them into the factors, a and b in the factors are the square roots of those numbers. So what is the square root of x squared? X. What is the square root of 25? 5. So we're replacing the a plus b, a minus b with x plus 5, x minus 5. Okay? And we can use that same strategy to help us with the one that Hannah did. So Hannah, you decided x cubed minus 27 was which special factor pattern?
I said, difference of perfect cubes.
Yep, this is a difference of cubes because x cubed is a perfect cube, 27 is a perfect cube, and they're being subtracted. Okay, so when you're deciding what to put in, you have to decide what your a and your b are. What is the cube root of x cubed? X. What is the cube root of 27? 3. Now, one of the big things that I see students do is sometimes they'll assign that cube root of 27 as like a negative 3. But the key about the special factor patterns is you just don't worry about the signs because the sign is all done in the pattern, right? So you always just call it like the positive value. Okay, so b is 3, and then you're plugging into the rule with our SOAP, a minus b, keep the same sign, times a squared plus ab, use the opposite sign, plus b squared because it's always positive in the back. Okay, so you substitute those in. I would rather you write 9 instead of 3 squared. Okay. And then Andrew, you did 4x to the 6 minus 49. You decided which special factor pattern was that? Difference of perfect squares. And so we were having a discussion on that side of room. How do we take the square root of something like 4x to the 6? So the square root of 4 is 2. Think about what's the square root of x to the 6. What x to what power times itself will make x to the 6? Has to be x to the 3rd, because then you add your exponents, right? So when you're looking for square roots of x to a power, you're really taking your power and you're dividing it in half. What's the square root of x to the 10th? X to the 5th. What's the square root of x to the 20th? X to the 10th. Because then you're going to end up adding your exponents, so you always just want half of it, because it will get doubled. If you were trying to take the cube root of x to some number, so like let's say it was x to the 6, what's the cube root of x to the 6? X squared. Because we have x squared times x squared times x squared, and 2 plus 2 plus 2 will be 6. So instead of dividing it in half, you're dividing it by 3. Is x to the 8th a perfect cube? No, because 8 doesn't divide by 3. Is x to the 8th a perfect square? Yeah, because it divides by 2, so it could be x to the 4th times x to the 4th. So you just kind of have to think about that in terms of those x terms, okay? But kind of be aware of that. Okay. 3 more for you to try, and I'm mostly concerned with the bottom two. So I think after doing x cubed minus 27, Hannah did that one, we could probably all do x cubed plus 27. I'll just do that one right now. The only thing that's going to change are my signs. Same, opposite, always positive. So it's the same answer as Hannah, but different signs. So go ahead and see if you could crack a play on to factor x to the 4th minus 81. Yes. Okay, let's look at x to the 4th minus 81. You know, anytime I have x to the 4th, it's not a perfect cube because 4 doesn't divide nicely by 3, so it is a perfect square. I do need to make sure the other number is a perfect square. 81 is a perfect square. Its square root is 9. And I have to make sure that they're being subtracted, which they are. So I could use difference of perfect squares. And I saw as I walked around, many people had x squared plus 9, x squared minus 9, and then I made my statement, make sure you have factored completely. What did I mean by that? I can factor x squared plus 9?
Like x squared, no, x plus 3.
X squared plus 9?
No, I lied.
Oh, so you're lying now.
Yeah. I mean, going back here, x squared minus.
You can factor the one that's a subtraction, right? Because it has to be another difference of perfect cubes. So I agree, Faith. It could be x plus 3, x minus 3, but x squared plus 9 I would leave alone. Okay. Good. So that's factored completely. And then what types of numbers do we have with 8x cubed plus 125? Perfect squares or perfect cubes? The cube kind of, or the x cubed kind of gives it away. Perfect cubes, right? 8's a perfect cube. What's its cube root? 2. So a is 2x. And what's the number do I multiply by itself 3 times to get 125? 5. 5 times 5 is 25. If I had 5 quarters, I'd have $1.25. So b is 5. I'm going to plug that into my rule for a sum of cubes. That's 2x, same sign, plus 5. And here I square a. What's a squared in this example? 4x squared. I'm going to get a lot of people who tell me 2x squared. Okay? You're taking 2x and you're squaring all of it, so you must distribute it, or you can think about it like 2x times itself, 2x, which will be 4x squared. Opposite sign, so it's minus. A times b is 2x times 5, so that's 10x. And then plus b squared, that'd be plus 25. Factored, and I'm done. Okay. So special factor patterns just require, some careful thought in the beginning as to what type of numbers you have. Okay. If you want to, you could always make a list at the top of your paper, perfect squares and perfect cubes. They're easy to make. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. Or 1 cube, 2 cube, 3 cube, 4 cube. And you know all the numbers, okay, that you're looking for. Okay, I'm going to breeze through some of the next examples, so I need you to be on point, writing, listening, asking questions. Got it? You can factor x squared minus 7x plus 10. We did that last chapter. With trinomials, I just use a sort of guess and check method. What did I multiply together to get x squared? X times x. Do I have factors on my last term 10 that add to make negative 7? Negative 2, negative 5. Factored. I'm going to change it for a polynomial and make it x to the 4th minus 7x squared plus 10. So the only thing I've changed really is the exponent on the first term and the second term. What do you think might change in my solution? Do you have factors of 10 that add to make negative 7? Yeah, what are they? 2 and 5. But I wouldn't want it to be x, because otherwise this would be x squared. I want them to be just numbers. Minus 2 and minus 5 make positive 10. So what must be in front? X squared. X squared times x squared will give me x to the 4th in front. And then this will give me a negative 5x squared. And this will give me a negative 2x squared, which will make negative 7x squared. Okay. So if it's x to the 4th, x squared in a number, you can factor it the same way. Okay. Now, don't forget about GCFs. What does GCF stand for? Greatest common factor. Greatest common factor. Always check for a GCF first. Okay. If I give you 5x to the 4th plus 15x cubed, before I check for perfect squares or perfect cubes, do they have anything in common? 5 and x cubed. So we can take out a 5x cubed, that's the greatest common factor. What's left over?
X plus
X plus 3. You can check if you're right by redistributing. It should be the same thing it was before. How do I factor it out? It's basically like you're dividing each of them by the GCF. So what's left over? Now, this should look familiar. X cubed minus 7x squared plus 10x. What's different? Now 10 has an x, and everything else has an x, so what should I do first?
take out the X.
Take out an x. Greatest common factor. Factor an x out. Then I'm left with x squared minus 7x plus 10. That's x minus 5x minus 2. We already did it. Now there's an extra factor, right? A third factor to get the cubic. Questions? Okay, the last one we need to look at before you leave today, and you'll get practice with this tomorrow, is factor by grouping. So go ahead and write down this polynomial, x cubed plus 2x squared plus 7x plus 14. What's different about this polynomial than all the other polynomials we factored before?
It goes 3, 2, 1. It goes all the way. Yeah.
Oh, it goes 3, 2, 1 constant. What else would you say?
There's 4 terms.
There's 4 terms. So use factor by grouping when you have 4 terms. When you have 4 terms, you can split up your polynomial evenly into 2 groups of 2. I'm going to use parentheses to split it up. These parentheses are not the same as like multiplication parentheses. I'm just grouping to separate my polynomial at this point. Okay? I'm not trying to multiply it all out. I grouped them in groups of 2, and now I'm going to ignore the last group. I'm only going to focus on x cubed plus 2x squared. Factor out a GCF. What can I take out both terms? X squared. And then I'm left with x plus 2. Okay. Now, worry about the second group. What can you take out of 7x plus 14? 7. Here's the thing. You have to, on the second group, take out a sign. Are you taking out a negative 7 or a plus 7? Plus 7. So you got to put plus 7 right there. Sign is important. And then you're left with x plus 2. Maybe make a note in your notebook, include sign.
Oh, we did set up the one.
Yes, you did. Now, what do you notice about these 2 groups of parentheses?
It's the same.
They're the same. So what I'm going to do, and I'll talk about it in just a second, I'm going to undistribute the x plus 2, which means I'm actually only going to write x plus 2 one time on the next line. And my other factor is made up of the coefficients that I factored out as GCFs. So my next factor is x squared plus 7. When I say I undistribute it, it's like I had this x plus 2, and I multiplied it by x squared, and then I took the x plus 2 and I multiplied it by 7. So both of them had an x plus 2, but I'm going to undistribute it from both of them, so I only write it one time. And then it's factored. You might check to see this if this is a perfect cube or perfect square. It's not, so this is my final answer.
That's how we figured out like the standard form, like for the 3 times.
Oh, how you did factoring for 3 terms? Yes, maybe we can do that next week. Show how factor by grouping works for trinomials. But you have to have 4 terms first. But I love it because
No,
it's, oh.
Like what we did was like, it was like x squared plus like 5x plus
6?
5.
Okay.
And then you go like x squared plus 3x plus 2x plus 5, and you just do the exact same thing. Like group it and then whatever. So what's
You write that down, Trevor, I'd like to see.
What's our winner for Friday?
Okay, so could you please write this down? This is your homework assignment for today. but
Yeah.